Alright, it's time to talk about light and color again. So just a reminder that color is a spectrum, as is all electromagnetic radiation. And so there isn't really, a cutoff as where blue starts and green ends, or when you're going either direction. Instead, it's kind of a flow from one to the other. And this goes for all wavelengths of light, so electromagnetic radiation. It's all just kind of a flow, so there is no distinct line between X-rays and UV. It really just kind of flows from one to the other. So really, all light that we see is composed of color. Even though the bulb comes out and it might look slightly yellow or white, it's because it's composed of all of the colors of light. So what we view as white is really a conglomeration of all of those together. Rainbows, so what forms a rainbow is actually taking the sunlight and it's splitting it up into the different colors, so we see the full spectrum. Instead of normally when our eyes take in all the colors at once, it kind of blends them all together and gives us a white color. But when you see something that's blue, usually it's just giving off blue wavelengths, or if it's yellow, it's just giving off somewhere in the yellow range of wavelengths. If it's a mix of colors, like maybe it's purple, you might have some blue wavelengths and some red wavelengths mixed in there. But we can view these different wavelengths by using what's called a prism, essentially. So a way that we can analyze light is by shining it through a prism. Now you guys probably already know this, but a prism takes light and it breaks it apart into its individual components. So instead of our brains kind of taking all of those wavelengths and meshing them down into one color, it takes it and separates out into its individual wavelengths or individual colors. So the way they would do this is by taking an atomic light source. And an atomic light source it's composed of usually just one element. And so it'd be something like neon gas or helium gas or sodium vapor, some kind of single element in there that they would then generate or pump electricity through, which causes it to excite the electrons and make light, and they would shine that light through a prism. The prism would separate that light into its individual colors, and then we could capture those on a screen that we would use to visualize everything. You can also do this with a flame test. When you burn different solids, you generate different colors of light inside of the flame. And the same thing, you can shine that light through a prism, capture it on a screen, and use that then to analyze the atom itself. So here's just a general example of what's going on. We have some unknown gas here, so some unknown element. We would shine its light through a prism, and the prism, it basically refracts the lights at different angles. And so instead of them all going through at the same rate, at the same angle, they would bend through and separate out. And by separating like this, it means our brain cannot put them back together. Our brain meshes them together when they're all in one, but once we separated them out with a prism, we can see the different colors. And so whatever this sample is, it generates 3 different wavelengths, some blue, some orange, and some red, which we would visualize as kind of this color when it's all meshed into one. But when they're separated, then we can see what the wavelength of each individual color is. Alright, so here's a picture of a screen from a hydrogen sample. So this is the hydrogen emission spectrum. This is the spectrum that hydrogen will always produce. We can take an unknown sample, we can do the emission spectrum test by shining on a screen like this, and if it makes a wavelength at 410, 434, 46, and 656, we will know that it is hydrogen. It's a fingerprint for hydrogen, really. Every element on the periodic table exhibits a distinct emission spectrum, and so we can actually identify elements based upon these spectrums right here. So if we have an unknown, they can burn it or they can put it in the gas discharge tube, and they can then calculate or figure out what element it is based upon the emission spectrum. In fact, they discovered helium on the sun before they ever discovered it on Earth using this technique right here. They actually stared at the sun essentially with a spectroscope, found a new fingerprint that they had never seen before, called it Helios or helium after the sun, and then that was the new element on the periodic table. So why? Why do they make the different colors? So just kind of a little bit of a review. As wavelength frequency change, so does the color. Okay, remember that, wavelength goes up, frequency goes down, and the color changes as well. But there's also a duality to light. So light isn't just a wave, it actually acts like a particle and a wave. It's kind of the whole Schrodinger's cat thing. And as wavelength frequency changes, the energy per photon changes, and it changes in those quantum amounts. Speaking of quantums, here's the Bohr model of the atom. So what happens in an atom then is, we're going to look at just hydrogen for now, because that's actually what Bohr did his original research in, and why we have the Bohr model, is there's electrons moving around the nucleus. So hydrogen has one electron, it's in the N1 level, sitting right here. If energy comes in, so if we put that electricity into a sample of hydrogen, or we put it in a fire, we're essentially putting energy into that electron. So photon of energy comes in, hits that electron, and causes it to become excited, which means it jumps up a level. So when an electron is given energy and it jumps up to a higher energy level, we will say that that atom is in an excited state. And so once it goes up there, this is like throwing a ball up in the air. It doesn't just chill up there forever. Electrons are lazy, just like everything else. They're going to go to the lower state of energy that they can handle, and so it's going to drop back down. When it drops back down, though, it releases energy. So up on top here, it has potential energy. When it falls back down, it releases that potential energy in the form of light. So if we imagine that electron that has jumped up to the excited state, it's going to fall back down, and when it falls back down, we say it is now in the ground state. When it falls back down, it releases energy, and it releases energy at a particular wavelength. And we can calculate that wavelength, or the frequency of this light, based upon that equation, E equals h times v. So the energy of that wavelength is going to be equal to Planck's constant times the frequency of the wave. And depending upon the amount of energy that it released, so if it falls from 1 to 2 or 3 to 1 or 3 to 2, it can have a different frequency, and a different frequency means a different color. So here is a diagram showing the visible spectrum of hydrogen gas. So when you have a sample of hydrogen gas in a gas discharge tube and you put electricity through it, you're generating 4 different colors essentially that our brain is seeing and meshing down into one. Those 4 different colors are happening from all these atoms at once, jumping, falling, falling, excited ground, exciting ground, and then they make the different wavelengths of color, different frequencies due to different energies. So if an electron goes from the 2nd energy level up to the 4th and then falls back down, it's going to generate this wavelength, which we perceive as blue. If it goes from the 3rd down to the 1st, it's going to generate this wavelength, which we see as green. We already talked about 2 down to 1 makes red, and from 4 down to 1 gives us that purple wavelength. All of these are going to be happening at once, and so we're seeing all of these wavelengths, but our brain can't process 4 different wavelengths, so it meshes it down, and so we see instead hydrogen as a slight pinkish color. Now, this is actually the data that Bohr looked at, and so Bohr looked at hydrogen gas through a gas discharge tube, found it on the emission spectrum, and then was able to figure out, okay, there must be different energy levels, and that's how he calculated these different energy levels for hydrogen, and that's where we got n equals 1, 2, 3, 4, and so on and so forth.